long before we could launch probes toward distant planets, before we could use state-of-the-art computers to track the movement of the stars, even before we had telescopes to help us look deeper into space, all we had to explore the universe was our eyes. For thousands of years, ancient astronomers studied the night sky just by looking up, and they learned more than you might expect. Today, we'll explore how the work of astronomers across history guided everything we know about the solar system, and why they've spent over 2,000 years figuring it out. Astronomers have been trying to understand our place in the universe since prehistoric times. Early on, they had tons of theories. Some believed that the Earth was a disk and the sky was a dome with all the stars on it. Others thought space was more like an endless ocean with the Earth, sun, moon, and stars floating in it. They also noticed patterns in space that helped them predict eclipses and the movements of planets. They just didn't know how any of it was connected. About 2,600 years ago, astronomers in ancient Greece began to put all these observations together to create the first models of the universe. Their earlier versions included a cylinder-shaped Earth and giant wheels of fire, but believe it or not, they were on the right track. Remember, these early astronomers didn't even have telescopes, but what they did have was math. And a lot of free time, so they quickly started correcting their mistakes. For example, there's a common misconception that, until fairly recently, people thought the Earth was flat. But thousands of years ago, these ancient Greeks used geometry not only to prove that the Earth is a sphere, but even to calculate its exact size. Of course, you may remember from our previous unit that a sphere doesn't perfectly describe Earth's shape. We now know that it's an oblate spheroid, which is like a sphere that bulges just a bit in the middle. But they were pretty close, considering the tools they had available to them. Then, in the 4th century BCE, a philosopher named Aristotle suggested that the spherical Earth must be at the center of the universe. This idea is called a geocentric model. Aristotle's geocentric model suggested the Earth stayed still while the moon, sun, planets, and stars moved in perfect circles around it. The geocentric model made sense to people. After all, it does look like the sun, moon, and stars are all moving around us here on Earth. But a model of the universe with Earth at the center didn't explain everything. Aristotle's model said that the planets all moved around the Earth in perfect circles. But as astronomers observed the planet Mars, they noticed something. Sometimes it appeared to be bigger and brighter in the sky. Other times it looked much smaller and dimmer. How do these observations prove that the geocentric model can't be correct? Pause the video here and record your thinking in your guided notes. If Mars were moving around Earth in a perfect circle, then it should always appear to be the same size and brightness in the sky, since its distance from us wouldn't change. But because it varies in how big and bright it looks, astronomers realized that Aristotle's simple geocentric model couldn't be right. In answer to this, a Greek mathematician named Aristarchus said, "Everybody, I think it's the sun at the center, not Earth." But that idea sounded so wild that everyone ignored him for a few hundred years. So even though it had some flaws, Aristotle's geocentric model was pretty widely accepted until around the year 100 CE, when an Egyptian mathematician named Ptolemy took the geocentric model to the next level. Ptolemy had a theory that each planet moved in its own small circle, while those small circles moved in bigger circles around the Earth. It's a lot of circles, but it did explain some things that Aristotle's model couldn't, like why planets sometimes appeared to move backwards in the sky. And Ptolemy's model was pretty good. It could even predict the positions of planets and the timing of eclipses. But Ptolemy's model still left some questions open. It just took another 1,500 years before anybody got the world to listen to their answers. Nicholas Copernicus was a Renaissance mathematician and astronomer who thought the geocentric model just didn't add up. In the early 16th century, he proposed a completely different model. Unlike when Aristarchus first suggested a heliocentric model over a millennia earlier, Copernicus's model gained more attention. While it still had flaws, such as assuming planets moved in perfect circles, it offered a simpler explanation for planetary motion, including why Mars appears to change in size and brightness in the night sky. If all of the planets are orbiting the Sun, why would it make sense that Mars's size and brightness would change throughout the year? Pause the video and record an idea in your guided notes. If all of the planets are orbiting the Sun on different paths, there will be times when Earth and Mars are close together, and other times when they are very far apart. This idea explains Mars's changing appearance in the sky. But this wasn't enough to convince many of Copernicus's closest colleagues. Most astronomers still favored the long-accepted geocentric model, and there was no observational proof that Earth was actually moving. Fearing backlash and ridicule, Copernicus was hesitant to share his ideas publicly, and his book, explaining the heliocentric model, was only published shortly before his death in 1543, nearly 30 years after he had developed the theory. But his ideas were the spark that astronomy needed, and led to what is now known as the Copernican revolution. The proof Copernicus lacked started emerging nearly a century later, thanks to Galileo Galilei. You may remember from a previous lesson that Galileo used a telescope to observe sunspots, challenging the idea of an unchanging perfect heavens. But this wasn't the only trouble he got himself into. In 1609, he turned his attention to the planets in our night sky. Why did this get him into trouble? What he saw provided strong evidence for the Copernican model, which was still not popular in 17th century Italy. Galileo discovered 4 moons orbiting Jupiter, clear proof that not everything revolves around Earth. He also observed phases of Venus, which are similar to the phases of the moon. But its series of phases as seen from Earth can only be explained if Venus orbits the Sun, not Earth. These observations directly contradicted the geocentric model. Despite his groundbreaking discoveries, Galileo faced fierce opposition and was even put on trial for heresy. Many scholars and religious authorities rejected the heliocentric model because it contradicted long-standing beliefs that placed the Earth at the center of the universe. However, his work laid the foundation for modern astronomy. Over time, as more evidence accumulated, heliocentrism became widely accepted. From Aristotle and Ptolemy all the way to Copernicus and Galileo, every influential astronomer's ideas had one key thing in common. Can you think of what it is? All of them were building on the ideas of the astronomers, philosophers, and mathematicians before them. Aristotle and the early Greek astronomers introduced us to the idea of a structured model for the solar system. Then Ptolemy refined it to explain new observations. Copernicus changed the structure altogether to fill in the gaps in Ptolemy's theory, and Galileo built on those ideas to guide his observations. In other words, scientific discovery isn't just about being the first one to notice something amazing. It's also about recognizing that we don't always get it right the first or second or 100th time around. In fact, the process of making a scientific discovery often involves questioning what we think we already know. And sometimes we learn amazing new things along the way. Be sure to complete the practice questions and extension activities to learn more about how observations made thousands of years ago, with nothing but the human eye, guided our understanding of the cosmos today. And always remember, you are out of this world.
Hey, hey.